Alrighty, folks, so we start the beginning of the end of our unit. There's actually 14 sections, but 13 and 14 go together as one big section together. And it's essentially all calculator work. Lesson 12, it's going to take me a couple days, maybe 2-3 days. I'm not sure how many because today's weird bell schedule, but it's transformations. And you already know almost all of it because you should have learned about transformations in at least 2 math classes before this one. And one of the great things about transformations is that they're the same no matter what function you're talking about. Transformations are transformations. They don't change. What you're looking at is almost all the different ways that a function could be affected. You could have multipliers on the outside. You could have addition or subtraction on the outside. You could have addition or subtraction on the inside, and you could actually have multipliers on the inside as well. It's not here for some reason, but it is in the notes. It says there are 4 types of transformations: dilations, reflections, rotations, translations. That's a total lie in algebra. We do not rotate diddly in algebra. Now, can we rotate graphs in higher level mathematics? We can, but it requires knowledge of trigonometry to pull it off. So no, there's actually only 3 classifications: dilations, reflections, and translations. 2 of these 3 are called rigid transformations. Rigid transformations keep the original size and shape. The only thing that can change is where the graph is and its orientation. So you could turn it upside down or you could turn it left, right, but you can't change its size or shape. I do want to introduce you to one of my favorite words in mathematics. Well, it's only introducing it to you if you didn't have me for Algebra 2 or Venice Middle School for Algebra 1. That word is Hyovas. And Hyovas stands for horizontal, inside, opposite, vertical, outside, same. What Hyovas does for us is it describes to us what kind of transformation we're dealing with, a horizontal or a vertical, where that transformation occurs, inside the notation or outside the notation, and what kind of effect it has. The opposite effect is what we expect, or the same effect as what we expect. Yes, sir?
What's the last 3 stand for?
Vertical, outside, same. So again, it's what kind, horizontal or vertical, which means X or Y. Where is it, in or out? And how does it act? The opposite of what you expect or the same as what you expect? Hyovas. So let's get to these first 2. Notice these first 2 are happening outside of f of x. They're happening outside of the function notation. That means these are both vertical transformations. They happen to the y values. So vertical transformations are your y value changes. Horizontal transformations are your x value changes. Notice that x is inside the parentheses. That's what I mean by an inside change or an outside change. So because this is happening outside, this is a vertical change. Vertical happens outside and has the same effect as it expects. This looks like your y value having k added to it. That's exactly what's happening. This looks like your y value having k subtracted from it. That's exactly what's happening. It does the same thing that it looks like. This and this, addition, subtraction, are the same kind of transformation. These are translations. Addition and subtraction will always be a translation. But these are specifically y translations because it's happening outside of the function notation. If you add a number to your y values and you're on the y-axis, you go up. That's why you would say vertical translation. You could say vertical shift. That'll work also. Vertical translation of k units. And if what you said was a positive number, that means you went up. You don't have to say shift up. You could just say, oh, vertical translation of 4 units. The interpretation is that was up 4. Now, if you say vertical translation of -3 units, the interpretation of that is down 3. College Board is not going to use the words up and down when they write their transformation questions. They're going to need the student to know that positive means up, negative means down. And that shouldn't be too difficult to understand because the positive y-axis is up and the negative y-axis is down. How does this kind of transformation affect the coordinates? Because here's the thing, no transformation changes a graph. Transformations only change coordinates. It either changes the x or it changes the y. So how do these transformations change your coordinates? They don't touch your x's because their y changes. They only change your y values. This one looks like it's adding k to your y values. It does. This one looks like it subtracts k from your y values. It does. There it is. So if adding or subtracting is always a translation, these two are also translations. But because the addition and subtraction is happening inside the function notation, I know it's sideways, but you see it's inside those parentheses, it's an X translation, a horizontal translation. It's changing the X values. Has anybody in the room ever had to break someone's heart and dump them? London, quick to raise her hand, proud of it, I see. One of the reasons why she dumped him or her, I'm not sure, I'm not making any assumptions here, is probably because they did the opposite of what she wanted. So she dumped them. So they are X's for a reason, because they do the opposite of what we want, right? Well, your X transformations behave the same way. They do the opposite of what we expect them to. This looks like you're subtracting h from your x value. You're not. You're adding h to the x value. And if you add a number to an x value, your x value gets larger. That goes to the right. So you would say horizontal translation of h units. This one looks like you're adding to x. You're not. You're subtracting. And if you take a value away from an x, it got smaller, which goes left. Now you don't have to say left. You can say horizontal translation of negative h units. In fact, that is the way College Board is going to present these kinds of things on your AP exam. There will not be direction words. They will either be positive numbers or negative numbers. It's up to you to know that the horizontal transformations are x transformations because the horizon starts the same way, it goes left and right. It's not an accident that it's called the horizon. It's because it appears horizontal. It's not, obviously, unless you're one of those crazy flat earth believers. It is curved, but it appears horizontal. So how are the coordinates affected? Only the x's are changed, never the y's. This one says add h, so it'll be x plus h, y stays the same. This one looks like you're adding h, you're not, you're subtracting h. X minus h, leave y alone. Okie dokie smoky. The last type of rigid transformation is a reflection. These two are reflections. One of them changes the x's, one of them changes the y's. Please realize that f of x is just a fancy way of saying the y values. This negative sign is outside. That makes it a y change. This says take your y values and multiply by -1. This says take your x value and multiply it by -1. To help you not struggle with which axis that's reflecting over. I'm going to draw this little picture up. You know what? How about we use this as the x-axis? So there's my x-axis, there's my y-axis. I'm going to take an f of x, and I'm going to put it right here. And I'm going to wrap it in a circle. There. Notice that all of its x values are positive, all of its y values are positive, right? If I make its y values negative, which way does it move? Down. And since f of x means your y values, making your y values negative puts the negative on the front of the f of x. But moving up and down, which axis was I forced to cross? The x-axis. So multiplying the y values by -1 reflects over the y-axis, x-axis. You could also say across the x-axis. You could say reflect in the x-axis. Just be aware we could say any of those three things. It could say reflect across, reflect over, reflect in. They all mean the same thing. And isn't that weird? Changing the y's, you have to say the letter x. Just remember, it's because it's a vertical motion which crosses the x-axis as you do it. Think of it as a vertical reflection. Never describe it that way, but you're allowed to think of it as that way. Moving vertically is only going to change your y values. Your x values stay alone, or stay left alone. The symbol on your y value changes. So if it was positive, now it's negative. If it was negative already, now it's positive. It literally multiplies the y value by -1. You know what? How about we write that? -1 times. There we go. -1 times y. That's what it does. Now if I come back up here, boop, 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 boop. If you make the x's negative, if you were here and you make the x's negative, I hope it's obvious that negative x's are over here, you'd be forced to move to the left. But every left-right change is a horizontal change. That's an x change. Look at the axis that I reflected over, in, across. The y-axis. So making the x's negative is a horizontal reflection, which forces you to cross the y-axis. The arithmetic result is whatever x was, you multiply by -1. Your y values are unaffected. If you ever see a negative symbol on any multiplier, because this is a multiplier, please realize that that negative symbol represents a reflection. Okay? Good with that? And if you're going to struggle to use the correct reflection description, draw this little picture for yourself. And x, I see, I went across the x-axis. Because it's so easy to say the wrong word. It is. Boop, 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 boop. Those are the rigid transformations. Now we'll get to the non-rigid transformations. These are your stretches and shrinks. Henceforth, known as dilations. You no longer need to use the word stretch or shrink. They are dilations. You could, if you wanted to, use the word dilations for stretches and compressions for shrink. But you don't need to. You could always just use the word dilation. Because dilation does not mean get larger. Dilation means change shape. Size, might be. Change size. Said the wrong word. So I know when you say that your pupils dilate, you say that they got bigger, right? But what do you say if their pupils get really, really small because the sun is really bright?
They're shrinking.
That's not what we say, though. We don't say they shrank. We say they dilated. You see, so the word dilation is not unique to getting bigger. Dilation just means changing size. Okay? He shouldn't have been called Ant-Man. He should have been called Dilation Man because he didn't just get small. Did you say that's not a cool name? Get out.
I would not go see Dilation.
You wouldn't go see Dilation Man?
Bro, that's not a cool name.
But Ant-Man is cool?
Yes.
Ant-Man.
He's like a top 3 superhero.
Top 3 superhero.
Dude, he's so cool. Doesn't he have, like, ant powers or something?
No. It's some bullcrap about conservation of momentum and energy. And it's baloney. It's baloney, okay? It's garbage. Talk to ants, yes. Because there's a power we all need. Don't bite me, ants. Okay, anyway. Let me hop over this one for a minute. Okay? And let me go to these. Notice for these two that the number A is on the outside. It's an outside multiplier. All outside changes are Y changes. So they are vertical changes. These are your vertical dilations. Those are your vertical dilations. You don't need to say, oh, crap. I just said I'm skipping over this one and I freaking put my brace right there. And it's on the video. Moron. Hate when that happens. These are your vertical dilations. You don't need to say compression. You could just say dilations. What do they do? Well, outside changes do exactly what they look like they're doing. They change your y's. How? This one multiplies your y value by a number. Oh, so does that one. So then what's the difference between a stretch and a shrink, a dilation and a compression? Well, did it get bigger or smaller is the answer. But when you do your descriptions, say everything's a vertical dilation. Don't wonder, should I say compression? No, always say dilation. All you need to do is then say the number you multiplied by. Both of these things can be categorized as a vertical dilation of factor A. Now you might have noticed, I said A and I didn't say the absolute value of A. But what does absolute value do to a number? Yeah, but what does it do to all numbers? What's with the number is negative? What does it do? Makes it positive. Here's what this is trying to tell you. You are not allowed to quote a negative number when you describe a dilation. Because a negative is its own transformation. So if you're going to describe it, let's say I do this. In words, you would have to say reflection. And you would also have to say dilation. But what does it do to a coordinate? Well, multiplying on the outside does exactly what it looks like. It changes the y value. It multiplies the y value by whatever number sits on the front. Now, if you want to know, did it get bigger or smaller? Well, if the number on front was bigger than 1, it got bigger. If the number on front was between 0 and 1, it got smaller. But you would just say vertical dilation, factor 1/2, vertical dilation, factor 3, vertical dilation, factor 5, vertical dilation, factor 3/5. See, that's the glory of just saying dilation. Because as long as you say a number bigger than 1, we all know it got bigger. And if you say a number between 0 and 1, we all know it got smaller. You would never say vertical dilation factor -2. Don't do that. That's wrong. If you're going to describe it verbally or written, you must describe this as 2 transformations. But mathematically, yeah, you just multiply by exactly what sits out there. You got a -2 sitting out there, then it's going to do this to the coordinate. Which is great. So if you just have to plot a new coordinate or find a new value, you just do exactly what it looks like. Verbal description is two things. Arithmetic, it's really just one thing. Okay? Now let's talk about these horizontal dilations. And I'm going to have to do it like this. There's a hole in the paper that's in the way, so I have to write it over here. Oops, I'm going to write it over here. Remember, they are our x's because they probably do the opposite things that we want them to do. Horizontal dilations do the exact opposite of what they look like they're doing. If I put a 2 in the front of this x, it looks like I'm doubling my x's. I'm not. I'm multiplying them by 1/2. If I put a 1/3 in front of my x, it looks like I'm dividing by 3. I'm not. I'm tripling it. Essentially, it's a reciprocal multiplier. Luckily, you don't, oh goodness, 2 hands went up at the same time. Did I make a mistake, Cooper?
Well, I was just wondering why that when you multiply it by something, it's divided, or you multiply it by 2.
You want to know why it's doing the opposite?
Yeah.
That's a very difficult question to answer. The best answer that I could give you is because in order to get to the y values that you're hunting for, you need an x, right?
Yeah.
So if you put a 2 in front of your x, think of it as you're getting to the x value twice as fast, which gets you to the y value in half the time. That's the best explanation I have for you on that one. So my band people are leaving. Bye, band people. Yes? No. Everybody else, we're here until 1:13. I still have 15 minutes. Yes? No, that's opposite reciprocal. Opposite reciprocal changes the sign and flips the fraction. Reciprocal just flips the fraction. Okay, I'm glad you said that. Hey, gentlemen, a reciprocal multiplier literally just means flip the fraction over to multiply. That's what that means. So why is it showing absolute values? Because again, if you're going to describe it verbally or even in words, negatives are their own thing. So if I write f of negative 2x, verbally, this is a reflection as well as a dilation. What does it do to the coordinate, though? It doesn't touch the y value, but it does multiply by the reciprocal of negative 2. The reciprocal of negative 2 is negative 1/2. So down here in these two, I'm going to write 1 over b, comma, y. Because the coordinate gets the whole multiplier, not just the positive part of it. The description is just the positive part of it. And this can be a little bit challenging for some people, which is why I'm thrilled about the fact that we can just say dilation every single time. We have to worry about dilation and compression. If there's a 2 in front, you're multiplying by 1/2. So that is a dilation of, I forgot to say times x. Oh, I'm going to pause this while he talks over the announcements. All right, the announcement is over. So those 2 hands went up because I forgot to write x? Okay, there, it's there now. I was trying to say, yeah. So verbally or in words, you don't quote a negative when you're talking about a dilation because a negative is its own thing. It is a reflection. But the negative would be part of the reciprocal when you're trying to find the new coordinate. There. So if you saw a negative 2x, you would describe it as a reflection and a dilation. But it's a multiplier of negative 1/2. Okay. Now let's talk about this thing. I am going to argue that this is not a true transformation. I'm going to argue that. Because what is it? What do you classify it as? It's hard to answer that question. And if you're going to say absolute value of f of x, why don't we say f of absolute value of x? Why not say them both? Why only one of them? So I'm gonna cover it because it's in the notes, but I am gonna double check on this. I don't think it's part of the AP curriculum, but we're gonna cover it just in case I'm wrong. All right. Here's what this says. This says the absolute value of your y values. What does it do to a graph? It takes any part of the graph that has a negative y value and reflects it up to the positive y value. So what does that look like? Do I have scrap paper here with me? Is this someone's test? Ah, there's her test. Let me just draw on the back of her test. Okay. If this is your parent function, what? Move it down? I was just drawing a curve. If this is your parent function, if this is f of x, then f of negative x, absolute value of x, says everywhere you had positive y values, the graph is straight. No worries. The graph is exactly the same everywhere you had positive y values. But everywhere you had negative y values, at that x, that y value better turn positive. So this vertex has the same x value, but now its y value is positive. That's what it does. It takes any part of the graph that was below the x-axis and reflects it to above the x-axis. Any part that was above the x-axis is fine. You leave it alone. So it does this. But how do you even describe that? You know, I don't even know how to describe that as. I'll just show you how it does. And what kills me is, if that one's in the notes, why isn't this one in the notes? If this is f of x, then why isn't this in the notes? I'm going to show you what that does. What this does is it says everywhere where x was positive, your graph is fine. But the moment your x is negative, you take the absolute value of it first and then plug it in. So you see right here, where let's just say this was at x equals 2. At x equals 2, I get this y value, right? So when x is negative 2, I better get that y value again. Essentially what it does is it duplicates the right side of the graph to the left side of the y-axis. It turns every function into an even function. And in pre-calc honors, we used to do this one. Which would have taken any parts of this that were, so it would have taken this blue one, and any parts of the blue thing that were below the x-axis, it would have bounced them to above the x-axis at the same time. So I don't know. I don't know about this one. I'll do some research on it. I don't think it's part of our curriculum. Yes? Not anymore, it's not. We got rid of pre-calc honors. As a district, we moved to AP only. Ask your question again. Why? Money, baby, that's why. Because the more kids that pass AP exams, the more money the school gets towards, score. It helps us get a higher score, which makes it easier to become an A school. Yep. No, because if you fail the test, we also get bonus points for you being advanced. So we get a bonus point for advancing you, and then we get a bonus point for you passing the exam. But if you don't pass, we still got the bump for you being advanced. So if we hadn't advanced you, it would have been like a net 0. But advancing you and passing, woohoo! Advancing and not passing, well, we still got at least some points extra. So that's why they do it. That's why we have so many AP and IB courses now. Anyway, it says, use parent functions for polynomials to describe how the graphs of each of the following functions will be transformed. State the types of transformations, graph the function. Essentially what it's saying is, compare this to the parent function, y equals x squared. Compare it to the parent function. Let me even graph the parent function. I'm going to do it as a dotted line. There is the dotted y equals x squared. It goes through 1, 1, and it goes through 2, 4, negative 1, 1, negative 2, 4. Okay? There's f of x. But this is what we're looking to graph. First, we're going to describe how this has to be transformed to become this. Then we'll graph it. Order matters. If you have multiple y transformations, order matters. If you have multiple x transformations, order matters. What doesn't matter is if you do the x's first or the y's first. That doesn't matter because the y transformations can only change the y's and the x transformations can only change the x. So don't worry about that. Let's take a peekaboo at the outside transformations. These are my outside transformations. These are my vertical transformations. Remember what I told you? Vertical, outside, same. Not only do they have the same effect, they follow the same order you would expect. And what order do we expect things to follow? The order of operations, PEMDAS. Yup. That means multipliers happen first. If you have multiple horizontal transformations, not only do they have the opposite effect as what we expect, if you have multiple of them, they follow the opposite order that you would expect as well. They follow SAD-MEP. But that's only if you have multiple X transformations. So multiple inside transformations are going to follow the order of operations backwards. For example, if I wrote this, you would talk about this part first, then that part. Because you follow SAD-MEP, order of operations in reverse. Okay. Now we come here and we follow the order of operations. This gets talked about first. This is a vertical reflection. And if you move vertically, do you cross the x-axis or the y-axis? X-axis. So reflect over x-axis. Then addition subtraction is always a translation. So reflect over x-axis, then vertical translation of, since this is going up, 4 units. If it was going down, we would have used a negative number. College Board will never give the words up, down, left, or right for their transformations. They'll give positive numbers and they'll give negative numbers. So here's what this does. It turns this graph upside down and then scoots it up 4. So imagine you've got it looking like this now. I know I'm not drawing it, but just imagine it. Because then we're going to do this to it. So this is an addition or subtraction, which makes it a translation. Since it's happening on the x's, it's horizontal. But here's the question. Do I add 2 or subtract 2? Add 2, because opposite. And if you add 2, that's to the right. So you just say translation of 2 units, because the positive numbers are to the right. You don't say right 2, because they're not going to say right 2. And if it was going to go left, you would have said negative 2. You won't get docked, but you have to understand what they mean when they don't say it. Okay? I won't dock you if you say the words, because they're still true. It just will never be presented to you that way. Okay? Let's graph this bad boy the way that we learned how to do in Algebra 2. What makes the inside equal 0? 2. So the vertex is at 2, whatever number is to the far right. 4. Our vertex is at 2, 4. That happens to be right there. And now, you can just plug in any other x value that you want to. What's a good x to plug in? 1. Sure, let's plug in x equals 1. 1 minus 2 is negative 1. Squared is positive 1. Make it negative, negative 1. Negative 1 plus 4, 3. So it's at 1, 3. That means there's also a coordinate at 3, 3 because, reflections over the axis of symmetry. And then just for a good parabola, let's plug in another x. How about the number 4? 4 minus 2 is 2. 2 squared is 4. Negative 4 plus 4 is 0. So this is your new parabola. What do you think about that?
Pretty epic.
Pretty epic, he says. All right, nerds, we're going to call it there today.